Welcome back once again. Today we want to be discussing on neighborhood and neighborhood system. Now, in the previous lesson we've discussed on the definition of topological space, subspace, relative topology, set operation in topology, talking about application point or limit point, talking about the interior point, talking about the boundary point, exterior point, and the closure of a set. Now, today we want to look at neighborhood and what neighborhood system in a topological space. Then what does it really mean by neighborhood system? Now let's look at the definition. They're saying that let P be a point in a topological space, X. And that's that a subset N of X is a neighborhood. It's a neighborhood of P. That's a neighborhood of P if N is a superset. It's a superset of an open set G containing P. Can you see that? Containing what? P. That is what you ask as what? Definition for a neighborhood. He said that let P be a point in a topological space X. Now, a subset N of X is a neighborhood of P if N is a superset. That is what they're trying to say is that if I have a point P taken is an element in what? In the open set. I know that now. And then it is also is contained in that N. Now, don't forget that our G's must be in that term. That is in the topology now. It's an open set here now. So let's say that if N is a superset of an open set G containing what? Containing P. That's all the necessary supersets that contain that G. That is a subset of now because what we call it a neighborhood. That you can say that N is the neighborhood of point P is the inverse of the relation P is an interior point of N. And we can go back to and get what was by what? Interior point. So the class of all neighborhood now of P in X, that is, you can look at the class of all neighborhood of P in X in N in X of P in X is called what? Is called neighborhood system of neighborhood system of P. That is all the classes of all those sets that contain P, that has P inside, referred to as what? Referred to as neighborhood system of P. That is denoted by what? You can say that this one of P. So that is why we have what? A set of people that contain this. So now let's get example on that. Let's have one or two examples on that. Let's consider. Look at the example now. It give us a clear understanding of what I was trying to say here. Look at the example. Look at the example. It said consider the topology, the following topology on X, and let's make it A, B, C, D, E. Can you see that now? I have a topology to be what? Set of X, empty set A, AB, ACD. You have set ACD. You have ABCD, and you have what? ABE. So these are the topology that we have. Now say that list the neighborhoods. The neighborhoods 1 of the point E. 2 then of the point C. Of the point C. That we have to list the neighborhood of each of the point C, E and point C. Then also you also can try for look for point A, B and D. I will do the other one E and C now. How do you go about it? Now, solution. Remember the definition of a neighborhood. It said that point P in contain what point P in open set G, which is now containing what in N. Don't forget that our N is the neighborhood. I got that now. N is the neighborhood of that P. So now, and don't forget that our G must be an element in what in the topology. That is, our G must be an open set. So now, based on this definition of neighborhood now, so you now look at what are those for point P. You want to find the neighborhood of point P of point E now. What are those open sets? What are those open sets that contains E? Let's check it now. The neighborhood. You know that that is the open set. The open set containing E are what? Let's go back. We have the X. What other one? That contains, we have what? A, B, E. So these are the two open sets that contains what? That contains E. Now, then the only superset of X is what? The only superset of X of that set X is what? Is also X. And this X is contained in itself. But what are the two supersets that contains A, B, E? Superset that contains A, B, E, superset of set A, B, E are what? One, we have what? A, B, C. A, B, E is also contained itself. What again? We have A, B, C, E. Are we following like that? Then also we still have what? A, B, D, E. They are also part of this one. Then also an X that contains the superset. Therefore, the neighborhood system now. Therefore, the neighborhood system of E. The neighborhood system of E. We now give us what? Of E. The set of what? X. We have A, B, E. We have A, B, C, E. Then we have what? A, B, D, E. So these are the neighborhood system of that point X. The neighborhood system of that point X. So those are the. So these are now the what? Neighborhood system of E. Neighborhood system of E. Now, the next thing we'll look at, let's check for the second one, C. What about the neighborhood system of C now? For point C. Now, for the point C now, so for point C, so what are the open sets that contain C? The open set that contain, that is your G, that contains C are what? Let's check it now. We have X, the open set that contains C. Yeah, what again? We have A, C, D. What again? We have A, B, C, D. And those are the open set that contain what? That contain C. So, therefore, the neighborhood system of C now, the neighborhood system of C are what? They are now this. So we have the neighborhood system of C will now give us we have X, we have A, C, D. Then we have what again? We have A, B, C, D. A, B, C, D. Then also we still have what? A, B, C, E. Yes, we still have A, B, C, E. Because also it's another, it's a superset for that neighborhood, for that open set. So we have A, B, C, E. So these are the how you can obtain the neighborhood system of an open set. So that's of a point, right? This is how you can take the neighborhood of its points of a point. Now let's look at another one here. Let's look at another result now. Neighborhood system. Let's look at the result. Look at this result here. Now this one says that the intersection. Look at it. The intersection. Let's say M, M of any two neighborhood. Of any two neighborhood N and M of a point P, is also a neighborhood of point P. So what do we mean? It's like we want to prove this is a result now. Let's say functional. Let's prove it. We want to show this. We are given that okay, if N is a neighborhood of a point P, then also this N is also a neighborhood of point P. Then it is also this N intersection PM is a neighborhood of that point P. So that is what we need to prove. It's very easy to prove. Now, since look at given that since it is given that N and M are neighborhood of point P, then I will see that. So then there exists open sets. That was what? Open set. Let's say G and H. Are you following now? G and H. Such that number one, your P is in G, which is sub of what? That is sub of N, and your P is in H, which is also what? A sub of M. Can you see that? So, which implies that S, we can say that my P is an element of what? G intersection what? H. I got that. Which also is subset of what? Square of what? N intersection M. So, since G intersection X is open set, it's an open set now, then I can now have that since it is an open set of N, then I can now say that HN intersection M is a neighborhood. It's a neighborhood of P. So that is just the simple proof. Just a simple proof that you can actually achieve that. So that was also a neighborhood for that point P. So I hope you get it very well. So that is very simple way you can actually solve the problem. Now, another result I want us to quickly prove here. Let's put that another result before we can move on to the next part of the work. Another one I want us to quickly look at is this. Let's check this one now. Any superset M of a neighborhood N of a point P is also a neighborhood of P. You can see that. So any superset M of a neighborhood N of a point P is also what? Is also a neighborhood. You know, it's very easy to prove now. If you look at it very well now, that is, if you look at it, since N is a neighborhood, of P. I know that. Then what happened? Then there exists open set. There is an open set in tau. I know that. Such that you have, by definition of neighborhood, such that you have P in G is sum of what? Sum of N. Can you see that? It's sum of N. So by hypothesis, don't forget that N is by hypothesis now. So by hypothesis now you have, and by this result, by hypothesis you can say that because M is a superset of N, that means you can pick that N is what? Is a sub of what? Sub of N. So so we can now say that. So this implies that I can pick this one as P element of G, sub of N, sub of what? So which also implies P is in G, which is sub of what? Sub of N. Can you see that? So hence, I can say that my M is a neighborhood. It's a neighborhood of P. So those are the way we can actually deal with what? A neighborhood of a set P. So very simple as ABC. Please make sure you do more and solve more questions on it. So thank you very much. Then before I go, now look at this result also. A set G is open if and only if it's open if and only if it is a neighborhood. It is a neighborhood of each of its points. I think you're going to do this one on yourself. That is, if you have a set G, it's opened. If and only if it's what? It's a neighborhood of each of its points. Of each of its points. So you know you can solve it and you have to prove the forward. That you have to assume that okay, if G is opened, then it's a neighborhood of each of its points. Now conversely again, if it's a neighborhood of each of its points, can we show that G is open? I hope you get that now. So it's something you can just prove it yourself. Just let me give a trial for you. So maybe in the next video I will try and prove it for you. Then you get it now. So just prove this one, and it's very simple as ABC. So thank you very much. Have a lovely time. Bye bye.